So we will take as our definition of the Dirac delta the following idea. So the Dirac delta at y, or centered at y, or the Dirac point mass at y, whatever you want. So this is the standard Dirac delta at 0 translated so that it's now at y. And it's defined by the following equation. The integral of f Dirac y with respect to x over some set I is going to be is going to be f of y if y is in the set, and 0 if y is not in the set. Okay, so in other words, integrating against the Dirac delta evaluates f at y. So it's an evaluation type thing. Okay, so the Dirac mass at y, as we saw in the last video, is the probability density function for the expected value of f of x, given that the probability that x equals y is 1. So it's like if we're looking at the probability distribution where you're definitely going to choose y. So the probability of choosing y is equal to 1. Okay. Now we look at a closely related function. So let's take u of x, so to be defined by 1 if x is greater than or equal to 0, and 0 if x is less than 0. So this is the graph looks like 0 up to 0, and then it jumps up to 1 and has 1 as the value forever after. And so this guy is the unit step function. Also sometimes called the Heaviside function. Whoops, if I can spell it right. Not because one side of the function's fatter than the other, but because named after Oliver Heaviside, who was an engineer that did a lot of work with this. Yeah, this Dirac delta actually comes from engineering. Okay, so let's see. So, theorem. The derivative of u is the Dirac delta at 0. And so let's look at a proof, and I'll give you two proofs. So this will be proof number 1. So first off, let's look at the integral of this guy. So if we integrate from minus infinity up to x, and so I'm looking at the case just one-dimensional because it'll make life easier. And let's look at the integral of u prime. So then what is this? Well, by fundamental theorem of calculus, this is going to be u of x at the upper bound minus the limit u of t as t goes to minus infinity. But if we look at the graph for u, we see that that latter part is definitely going to be equal to 0. And if we look at u of x, then u of x is going to be 1 for x bigger than 0 and 0 for x less than 0. Okay. Meanwhile, on the other hand, if we look at the integral from minus infinity up to x of delta t, then what do we have? Well, so this is the same thing as the integral from minus infinity to x f of t delta t dt. If we take f of t to be identically equal to 1, right? So it's just like sticking a little invisible 1 in front there. And so then the definition of the delta is that it evaluates the function at the point that you're at. And so right now we're at 0. So this is going to be equal to, well, we're going to evaluate, it's going to be f of x for x greater than or equal to 0, and it's going to be 0 otherwise. And f is given by 1, so it's going to be 1 if x is bigger than 0, and 0 if x is less than 0. Maybe just to make this match up a little bit more closely with the definition, this is going to be if x is in the set from minus infinity, sorry, if 0 is in the set from minus infinity to x, and this is going to be if 0 is not in the set from minus infinity up to x. Okay, and so that equals this. And then you notice that these guys are the same. Okay, so that's one proof for you. For the second proof, let's let the interval from a to b be any interval, any open interval containing 0. So a is strictly negative, b is strictly positive. And suppose f is a smooth function, so differentiable, with the which vanishes at both endpoints of the interval. And so the interval here could actually be the entire real line. A could be negative infinity, b could be positive infinity, whatever. Okay, we just need that. All right, so then let's look at what happens when we've got u prime and f together in an integral. Well, by integration by parts, I can shift the prime to the f, and all I have to pay is a minus sign and a boundary term. And let's see, so based on the condition we had that f vanishes at the boundary, then we have that the first part is going to go to 0. And so then if we look at the other part, this is going to be, so we've got minus the integral from a to b. So I can split that as the integral from a to 0 times uf prime dx plus the integral from 0 to b uf prime dx. And then we look at the definition of u, and we see that for the first part, this is where u is equal to 0. And for the second part, this is where u is equal to 1. And so that first integral is gone. And for the second integral there, I can use, well, now the integrand is just f prime, so I can use fundamental theorem of calculus. And so this is going to be f of b minus f of 0. And I guess if I'm being strictly by the book here, I should replace that with the limit as that goes away. But then again, we see that that limit is going to vanish. And so the whole thing amounts to being f of 0. Whereas if we go back to the definition of the Dirac delta, that's exactly what this is. And so since we've established now this inequality, or sorry, this equality, for any smooth function f that vanishes on the boundary, we get u prime equal delta. Okay, so there's two proofs that the derivative of the Heaviside function is equal to the Dirac delta. Now, if you notice something about both of those proofs, the entire proof was carried out inside an integral sign. And that's exactly right. That is how we make sense of the meaning of the Dirac delta. We keep it inside an integral sign. It means we're looking at things distributionally. So this equality right here, this is not equality in the normal sense of pointwise equality of functions, because these guys are not functions. They are measures or distributions. And so the notion of what it means for two of them to be equal is a little bit different than for functions. And the way we say that they're equal is if we say, oh, well, if you integrate any function against them, any nice smooth function that vanishes at the endpoints against them, then you get the same thing.